Hi, everyone. Today what we're going to do is we're going to jump in and start working through another type of transformation. And you can see from the title today, we're going to talk about reflections. So I'm going to act as if we have no clue what a reflection is as we begin this process. And I think we should be able to kind of add in this second transformation relatively easily today. There's going to be a few things we got to focus in on in terms of notation, and there's a few things to be kind of aware of and focus in on in terms of graphing. But I think today should be pretty smooth. So you have our practice handout or our lesson sheet with you. What I want you to do is to try to create the exact same picture as what I have on my graph on Desmos. So you need to hop onto Desmos. I have listed for you in the top left what your domain and your range should look like. And what I want you to do is to try to create that exact same picture on Desmos. Okay, the exact same picture. Now, I've got a couple stipulations. You need to use functions. Okay, it has to be functions that create that picture. And that's it. Okay, go to it. What I want you to do, keep playing around with Desmos as best as you can. And when you think you've got something, then I want you to unpause the video and we'll kind of progress. Struggle through it a little bit. Okay, don't just quit as soon as there's some doubt. Play through. This could take 5 minutes of playing around on Desmos. Okay, your job, get that exact same picture. Okay, good luck. Pause the video now. Okay, if we are back, then that means we have a picture that matches up and we just want a little confirmation. Or maybe we've timed out at like 5 minutes and we've kind of said, okay, I've reached my peak. Now I need some help. Okay, we're going to take a peek on Desmos and see if we did match up. Okay, so hopefully that picture is what you have on your screen. I'm just going to maybe guess that we don't have the same colors. So in terms of playing around with Desmos, I would love it if we had that picture. However, I just need to draw your attention, that little stipulation. I want you to make a note that if you have typed into your function menu, y squared equals x, I want us to be very clear that that is not a function. If I was to sub in one value for x, I could get multiple values for y, and therefore it does not satisfy the 1-to-1 ratio. Okay, the way that you can tell is because if I was to take the square root of my y to get my y all by itself, then I'm going to have the square root of x, and because I need to have a plus or a minus, because when I take the square root, I could have two answers, you can see that that purple is not a function. So as we're working our way through, we have to be very careful of that and make sure then that we don't have anything that's not a function. Now, I may have given something away a little bit in that purple, but I hope that helped. Okay, if you want another shot at it, then I'm going to ask you to pause it now. Otherwise, we're going to play a little bit and we're going to check out and see what our functions should be. Okay, so what we're going to take a peek at then is we're going to go through and I'm going to pull up the equations for this. So I want everybody to take a look at my function bar. And if we were able to go through and deal with that, then I think we've got a great picture. Now, I know that this is, I don't know if I want to say like advanced on Desmos, but it's an extra feature, the ability to change the color of your function. That if you ever need to do that, what we do is we select a little cog up in our function menu. So if you select the cog button, it's now going to go through and pull up some options. You'll see on the right side, you can delete a function, you can copy a function, you can put it as a table. But on the left side, if you just select any of those little colors, then you can change your graphs to any of the colors that you like. You can actually go through and change your graphs to dotted lines or dashes, dotted lines, and so on. So you can even change the thickness For me, I'm going to keep it pretty standard, but what I'm going to do is I'm just going to change all my colors back to other colors, let's say, to give us the option to maybe see how each of those functions all come together to give the picture that I asked you to try to match. So I am hoping that everybody was good with the red function, and you are good now that you see the red function because you recognize that that's our square root function, and that's one of the base functions that you're responsible for. Now, if I play around with that, then maybe I come in on the blue. So what I'm going to actually do is delete the green and the purple. And I might argue that us playing around with the blue could have been something that we had background with. I'm going to actually eliminate all of these functions. And I'm going to punch in a function that we should have had in our back pocket from last year. There is your good old parabola. And with a little bit of experience from last year, then we could have known that if I was to punch in a parabola with a negative out in front, we tend to think of that as a parabola that maybe opens down. But if you take a look at the change in the graph from the black graph to the red one, then you might see that we've flipped it across the x-axis. And so the formal way that we could talk about that is we have reflected it across the x-axis. Don't use the term flip. Reflected is proper terminology. So if we see that, then maybe we had that in our background and we kind of go, oh yes, with our parabola. And that may have led us to adjust our function with our square root graph. So if I just punch in my good old square root function, and now if I want the function on the other side of that x-axis, then I can punch in my negative square root function. Now, for anybody who punched in y squared equals x, you'll notice that you get both of those graphs. The problem is, combined, they don't represent a function. Combined, they wouldn't pass the vertical line test. However, independently, each one would be a function. If the green wasn't there, the blue graph alone would be a function, and same thing for the green graph. Okay, so then you just start to play and you say, well, but how can I get the graph on the other side of the y-axis? Well, if putting an x out in front of the root reflected it across the x-axis, then maybe putting a negative inside, and I missed my equal sign. Putting a negative inside the function. And so all of a sudden then we see it on the other side. Now, if we were to do a quick little domain and range exercise, look at your blue graph. Our base square root function, we know, has a domain of x is greater than or equal to 0. Because our x is underneath the roots, that means that we have to sub in 0 or positives to be able to get a y-coordinate. If I subbed in negatives, I can't calculate the square root of a negative number, so my graph only exists on the y-axis and to the right. Well, if I want to change that, then what I do is I change the sign of my x. So take a look at your purple graph. Notice that by me putting a negative x underneath my root, now if I sub in negative values for x, the negative times the negative will give me a positive value, and I can calculate the square root of positive values. It's that I can't put positive values in for x anymore because the negative will switch the sign. So that's what allows me to create my purple graph. And then maybe we just end up getting kind of a combination of the two. For me to go from that quadrant 1 graph and try to create a quadrant 3 graph, then maybe what I say is, okay, let's reflect it across the x-axis. But then that's going to give me my green graph. Now what I need to do is to take my green graph and reflect it across the y-axis. So if I put my x in here right now, that's what causes the black graph to lay on top of the green. That is my green function. You can see it up above. But if I now put a negative out in front of that, I reflect it across, and now I have the picture that I've been asked to match. So hopefully we're able to go through that process and get down to that. If not, we can now see how we can get there. And hey, maybe we had an extra little Desmos activity on how we can change the colors of graphs and how we can create dotted lines or dashed lines. Hey, if we need to use Desmos to come up with some of our graphs that have asymptotes on them, maybe that's how we can draw our asymptote. So we've covered a lot of stuff at the beginning here today. What I want to do now is make sure that we can kind of nail out some key theory. Okay, so if we hop back just onto our handout, then there's a couple things that I want you to get down. The first thing I want you to notice is the star on the left side. That's us coming back to that generic function that we started to build last time with our stretches. So as we examine that star, and I'm just going to erase that star now, and maybe just box it in to draw our attention, can we make sure that we get down that generic function? F of x equaling a times f of p of x. In that form, if we call the a value out in front multiplied inside value p value, then we can draw on by hand our square root functions being reflected. And then below that set of axes, I want you to focus in on the green. That green star, let's make sure that we can sum up what we found today. That if the a is the value that's out in front or outside the function and attached by multiply, if it was negative, so a is less than 0, then we reflected our graph in the x-axis. We found that if we change the p-value to a negative, so the value that's multiplied on the inside of my function, if that value was negative, p is less than 0, then we had a reflection in the y-axis. Now, you'll also see the last part in purple on the bottom right corner. Can we please put a big star and then our inside versus outside statement about our transformations? And you will find that that's consistent with what we dealt with our stretches. Notice where my a value is. My a value is outside my function, and outside affected my graph vertically. Now, I'm just going to draw on the arrows on that outside. That when I changed the outside of my function to a negative, I went from my quadrant 1 square root function and I reflected it across the x-axis. So you'll see it explicitly. I was 2 units above, I'm now 2 units below. And you'll notice that all of my values were reflected the same distance on the other side. Now I'm just going to get rid of those blue. So for us to make sure that we're good, that I am reflecting outside, therefore vertically. Just don't make the mistake of saying, hey, well, if I reflected it vertically, then that must be the y-axis. No, I'm reflecting it in an axis or across an axis. And so if I reflect it vertically, then my positive y coordinates now become negative. That means I'm crossing the x-axis. What we see in that reflection is the term equidistant. Notice that all of my points are of equal distance on the other side of my reflection line. Okay, if we now focus in on the inside, my p-value, Inside means horizontal. So if I reflect my graph horizontally, then I need to take a point that was somewhere to the right and reflect it somewhere to the left, equidistant on the other side. That means I'm reflecting it across my y-axis. So notice that that inside versus outside relationship is true for reflections as well. That's nice because that makes it universal. Okay, pause the video if you need a moment to get all of that stuff down. As soon as you're ready, then let's jump in and take a look at the bottom part of that page. Okay, so what you're going to see on your page is completely blank. And what I would like you to do is just to take a moment to copy down what we have on our graph. So let me explain first, and then we'll take a moment to do that. What we're going to examine is the red function that we wrote up on the top. So I'd like you to fill in the blank and just complete f of x equals 2x plus 1. There's our good old line. Now, you'll also notice that on each one of those graphs, those grids, we're going to graph the function f of x. So I've just gone through and I've put on our base function in each case. So there is our good old line. It has a y-intercept of 1 and a slope of 2. Then on each grid, we're going to graph a reflection of each one. So on the first grid, you'll see in the blank space, we're graphing f of x, and we're going to graph negative f of x. On the middle grid, f of x and f of negative x. And on the final graph, we're going to go through and we're going to put down negative f of negative x. So what I would like you to do is to take a couple minutes. But let's pause the video now and let's work our way so we have that sitting on our page. Okay, pause it now. Okay, we're back. So what I want to do now is I want us to work our way through the first grid. Okay, the first grid. So we're going to graph negative f of x. Now, we know how to interpret that negative now. That negative is outside the function. Outside is going to affect it vertically. If I reflect my graph vertically, then it has to cross my x-axis. So I'm going to choose any point that's above my x-axis and reflect it down below. So maybe I take the y-intercept. It was 1 unit above. It gets transformed to 1 unit below. I pick any other point. Maybe I look at my graph and I see that I go through the point 1, 3. So I'm going to reflect that. It was 3 units up. It's now going 3 units down. My point was at 1, 3. It's now reflected to 1, negative 3. And so on and so on. But if I'm going to reflect across the x-axis, then that also means that any points that were below the x-axis are also going to get reflected above. So let's take a look at this point down here. It would be at negative 3, negative 1, 2, 3, 4, 5. Negative 3, negative 5. What I'm going to do is I'm going to reflect that point. So it was 5 units below. It's now going to go 5 units above, equidistant on the other side of the axis. So I go to here. Well, I have enough points now to be able to connect those with the pattern I see. I'm now going to have my line yikes. And we come in on something like that. And that would now be the graph of negative f of x. Now, we do get a little confirmation that we think that that graph's probably pretty accurate, because notice my invariant point. My reflection and my original graph intersect on the x-axis. And that should make sense. Any point that was on my original graph, my red graph, that's on the x-axis, Well, if I try to reflect that across the x-axis, it's not going to move. Nice. I get a little confirmation that that's probably the correct graph. Okay, what I'd like you to do is now to try the middle graph on your own. So I want you to go ahead, pause the video, and now try to graph f of negative x. Okay, pause it now. Okay, we're back. So let's just get a little confirmation of our picture. In the middle graph, I need to graph f of negative x. So the negative is on the inside is horizontal. So that tells me I have to reflect it horizontally. That means reflect it across my y-axis. So any point that's on my y-axis should stay the same. Anything that's to the right of the y-axis, for instance, that point there is 2 units to the right, it has to get reflected 2 units to the left. So that point should finish, right here. Well, this point was 1 across, should become 1 across. Well, now any point that was 1 unit to the left should become 1 unit to the right. And maybe if I go all the way to the bottom, I'll put the arrows back on again. That point was 3 units to the left. So if we now go 3 units to the right, that would be the location of that transformed point. So let me just delete out that arrow. There we go. And that should now get me out to here. So if we were to go through now and connect all of those points with a straight edge, and I'll do my best, that we should now get, I think that's a better line than the last one. Looks a little wobbly with my straight edge on the iPad. That we get down to there. And same thing as what we discussed before, I get a little confirmation that what we have as our invariant point is the point that is on the line of reflection. Nice. If I'm reflecting it across the y-axis, then any point that was on the y-axis does not change. Okay, that should give us a little confirmation with that one, and we should be good now to try to tackle the last one. Here's the thing I'm going to say. I want you to try to do it without using an intermediate graph. So I'm going to help out a little bit that we should be good that this this negative out in front, we understand what that does to our graph, reflects it in the x-axis. We understand that this negative on the inside reflects it in the y-axis. What I want you to try to do is perform both of those transformations to any of your points and draw the purple graph that would be negative f of negative x. Try to go directly to that and not draw a middle ground graph where one and only one of those transformations has been performed. Okay, try to do it all in one go. So you're going to go through, you're going to produce a picture of that purple graph. Okay, give it a shot. Pause the video now. Okay, we're back. So we're going to go through and we're going to try to tackle that same action. So the first thing maybe I do is I deal with my, let's say my intercept. That's a nice easy point. I have a y-intercept of 1 on my red graph. So I need to reflect that across the x-axis. So I'm now going to be 1 unit below the x-axis. And then when I reflect it in my y-axis, it's not going to move. So my finishing location with both transformations is going to be there. Okay, I'm going to pick another point. Now, this point didn't come through on my red graph very much, but I have the point there that exists at 1, 3. Okay, I'm going to put an X there. There's my original point. Maybe I do my reflection in the x-axis first. So I was 3 units above, so I need to reflect it 3 units below. But now when I look at that, I am 1 unit to the right of the y-axis I would now have to reflect it 1 unit to the left. That would be me performing both reflections. Reflected across the x, then reflected across the y. Okay, I can get rid of all those arrows, and I can just do that. So let's reflect it across the x, across the y, and there's my finishing position. Okay, maybe what I'm going to do now is I'm going to come all the way down here, and I could do the exact same thing. However, maybe it's important for me to see that it doesn't really matter what order I do my reflections in. That if I was to go through and reflect it across my x, so 5 units below takes me to 5 units above, and then reflect it across my y, so 3 units to the right becomes, to the left becomes 3 units to the right, I finish here. Well, I could have got to that exact same location if I did my reflections in the opposite order. Maybe I reflected across my y first. 3 units to the left becomes 3 units to the right. Now 5 units below becomes 5 units above. And I come in right to the same spot. So that's important for us to know, that as we work our way through and deal with our reflections, it doesn't matter what order I reflect in. I just erased too much. Let me get rid of all of that. And we should be good that regardless the order that we reflect that in, we should be coming in right there. Okay, I have enough points now to connect those and be pretty confident in my shape. And hopefully when we do that, we get something, and I'll do my best to draw a straight edge on this iPad, that looks like that. Now, I didn't do a good job of labeling on the last graph, and now I'm going to put in my label on my current graph. There we go. Okay, hopefully we can see that in this instance, we don't have any invariant points. That after we did both of those transformations, everything moved. Good. Okay, we have that, and all I want to do is I want to take a moment to just go through and address us dealing with the algebra of this. Really, I just want us to get a connection between our picture and our algebra that I think is going to help us with our understanding. So down below that, let's jump in and do one more activity. All I've done now that you see is I've just kind of shrunk it down on my screen a little bit, just so we can have a little extra space down below. If you can put a little star down below like I did, and just mark that we're just going to deal with our algebra a little bit. Then what I want to do is I actually want to take the purple notation and just actually treat this as if we didn't even have the picture. That is, if I had the statement negative f of x, what does that mean for my function notation? Well, if we go back a few days, we should be good to interpret that. That what that says is make your f of x function negative. So I'm going to make my entire f of x function, which is 2x plus 1, negative. Well, now that I do that, I can go ahead and simplify it. And I just want you to take a look at that graph. And notice that we get a little confirmation that my blue equation matches my purple graph. That would be a line that has a y-intercept at -1 and a slope of -2. So notice everywhere along that purple graph, I am going to the right 1, down 2. So notice that my blue equation matches with my purple graph. There's a little confirmation that what we did graphically, notice we paid no attention to the equation of our red line to produce our purple graph. What we did graphically matches up with our algebra. Notice when we did the blue, I wasn't paying attention to my picture at all. I was simply dealing with my algebra. So just a little confirmation, we get down to the same thing. Okay, I'm going to put a little wavy line in. We can do the same thing in our middle graph. Focus in on your notation, f of negative x. Well, what does f of negative x mean in function notation? It means, back in my original function f, replace my x with a negative x. Wherever I see my variable, replace it with a negative x. Now that I have that, I can simplify my function, so that would become a negative 2x plus 1. And if I was to graph that, I would notice I get a line with a y-intercept of 1 and a slope of negative 2. And again, we just get a little confirmation. Okay, I want you to go through and tackle that third one on your own. So you interpret the purple function notation and just deal with the straight algebra. You should be able to see what we should match up with in the end. Okay, pause it now. Okay, we're back. So I can then deal with my negative f of negative x. That tells me make the entire f function negative while at the same time replacing my x with a negative x. So wherever I see my variable, replace it with a negative x, and at the same time make the whole function negative. Multiply the whole thing by a negative value. Okay, the rest is just simplifying. So maybe I leave that negative out in front. I don't know. Now I can go ahead and fully reduce it. And we get a little confirmation that I should have a line with a slope of 2 and a y-intercept of negative 1. And there we go. Okay, that's it for today. I think we should be good in dealing with our reflections. We should be able to deal with the algebra like we just finished off with, and we should be able to deal with it graphically. We should be able to see a negative value in either location and be able to interpret that correctly as a reflection in the x-axis or a reflection in the y-axis. Okay, your job now, jump in and get some practice and make sure that we're really comfortable with it. Okay, good luck.